Now, in school or in college, you'll see in textbooks, and you've been told that you cannot integrate x to the minus 1, i.e. 1 over x. Now, if I did that, I'd get the integral of x to the minus 1 dx. Right? Now, if I wanted to integrate that, I'd add 1 to the power and divide by the new power, i.e. I get x to the 0 divided by 0. Now, what is x to the 0? 1. Divided by 0? We don't like dividing by 0. So clearly, it's not using the rules we know. So that ain't true. However, where it gets sneaky with this kind of question is 1 over x is actually a separate function in itself. Now, the way I like to prove it is by drawing the graph of 1 over x. Now, 1 over x is a key graph that you would have learnt in the Graphs and Transformations playlist, which I did for you a long while ago, so you might be able to find that. But actually, this is a common one where this integrates to the natural logarithm of the modulus of x plus constancy of integration. Now, why? Well, if I drew the graph of 1 over x, I get something like that and something over like that. And I could quite happily say integrate between minus 3 and minus 2. Well, I'd have log of minus 3, but I'd have to then mod that because then that's technically not an area. I'm actually going to get a positive y out because there's a reflection of it because 1 over x is reflected in the axis of y equals minus x. You get that reflection going on, don't we? So the way to prove it is if I said, well, how do I prove y equals natural log of x? Where x obviously has to be greater than 0 because we can't define log of 0 yet. So I'd exponentiate both sides, so I apply e to the y equals, now e to the log x will just give us x, using our products of e and natural logarithm. I can then use what's called implicit differentiation, which if you've watched the implicit differentiation playlist, and the further differentiation playlist, you'll know what's going on. Obviously, if you're on the AS, then this will just be a proof that you just have to learn without it where you're told where it's really coming from, because it's in the A2 implicit differentiation. So I get e to the y, the derivative of y is dy by dx. That's equal to the derivative of x, which is 1. Now dy by dx, get that on its own, that's 1 over e to the y. What is e to the y? Well, e to the y was just x, i.e. I get 1 over e to the natural logarithm of x. Natural logs cancel out, and I get 1 over x. Now this is quite sneaky because you're not really taught it. You're taught, oh, you can't do x to the minus 1, you can't do integration with that. But actually, you can. And it's one of the sneakiest things you've ever seen, because when you go ahead and integrate things like the integral of 1 over x between minus 3 and minus 2 dx, you have to have the natural log of mod x plus c. Plus c is one of the definite integrals. So if I wanted to integrate between minus 3 and minus 2, obviously my level graph will help me over here. So I'd have log of modded of minus 2, which is 2, take away log of modded of minus 3, which is just 3. So obviously combine the log laws will give us a log of 2/3. So the problem with integrating x to the minus 1 is because it's its own function that you've been working with for a long while, and when you actually come to integrating it, it's actually really nice because the integral of 1 over x is just a function log of x. Now later on you'll be integrating things like log of pretty much anything like 2 over x and 3 over x and 4 over x, and you can just stretch this graph, but it's the same thing, just with a number out the front. So it doesn't change very much, but it is quite nice because then we can use it in the ideas in further maths when we look at solving differential equations, which obviously that playlist is still going on at this time of filming this, right? So This is the idea of why x to the minus 1 you cannot use using your properties of integration.